In all the previous lectures, we only discussed about the theory of the quantum computing. In today's lecture and the next lecture, I will actually introduce the real quantum computing device. And then of course, here I just listed a few of the possible physical implementation of the quantum computing. But this is not complete. Yeah, there will be all other options, but these are some of the popular options. So let me give you a few a brief introduction to some of these. The first example is the photon, and then you are already familiar with the concept of the photonic qubit. So in early lectures, two of the popular example for the qubit was either the polarization of the photon or the electron, the quantum state of electron in the two-level atom. And then the first example corresponds to the photonic qubit. Of course, in a single photon, there are multiple properties, not only the polarization. So people can utilize multiple mode or multiple degree of freedom in a given single photon. So and as you can see in many of the example when I explained about the properties of the qubit, the photon is a very nice qubit, except that there is some kind of limitation that when you are trying to implement some kind of 2-qubit gate like this one, then there is the result is not deterministic. So and then there are also other approaches to make it more deterministic, but it also requires a lot of overhead. So I would not say that I would not say that it is impossible to implement the quantum computing, but there is also some limitation with the photonic qubit. So depending on your application, photon might be a good solution as option, or sometimes it might not be as good as the other options. And then, of course, the other options are not good for the communication. So photon is a very important medium to create the entangled state between remote qubits. And then, so each of them has their advantages and then disadvantages. Another option, which is very close to the concept of the two-level atom, so which was the ground state and then excited state, and then the in such kind of case, this is somehow simplified model of the hydrogen atom. And then if you start with some kind of neutral atom, but if the you know that regular atoms, if you learned about the periodic table in chemistry, then there will be multiple shells, and then there will be a lot of electrons in a single atom. However, what really counts, or what really matters in terms of the chemical reaction, is the number of the electron in the outermost orbital. So neutral atom generally uses such kind of property. So with if you are trying to implement this kind of two-level atom system, then what you do is you start with the neutral atom in the first column of the periodic table, which means that the first column means that the number of electrons in the outermost orbital is, I think, just one. So that's a great implementation. But one of the challenges with the neutral atom is that you want to trap as many neutral atoms as possible, and then only the single atom in each of the sites, for example, in this case. And then there is some kind of challenge. So instead of using the neutral atom, another approach is using the trapped ion. So trapped ion is very similar to the concept of the neutral atom, except that the entire atom will have some additional charge, and then by having additional charge, we can actually trap each of them using the electric field only, and then the and then still the number of the electron in the outermost orbital will be still one. So internally, the quantum state of the electron is similar to the neutral atom, but it also has its own advantage. And then also, there will be a disadvantage. And then unfortunately, I have limited time to explain further about the ion trap in today's class. But at the end of this semester, if some time allows, then I will also give you more introduction or more overview of the trapped ion system, because that's what my research group is working on. And then let me just move on to other types of system. Another popular example of the quantum computing is by using the superconductor. And then the superconductor is not a single atom, so you might think that it has nothing to do with this two-level atom. However, if we have some kind of superconductor, and then depending on how you design it, then you can actually make a quantized energy level inside the superconductor. And then what that means is that when we first learned about this two-level atom, all we care about is the energy difference between these two, and then whether the electron really goes up or down. What really matters is the energy state. So as long as the superconductor can create such kind of quantized energy level, then in principle they can be also used as a qubit. So you might consider that the superconductor is the extended concept of the two-level atom, and then and then I will also give you more example about the superconductor qubit in the next pages. And then another popular example for the quantum computing or the qubit is either using the quantum dot or the MV center. And then quantum, you are also familiar with the terminology quantum dot, because some of the company are making the display out of the quantum dot. And then the fact that you can actually they can create the photon out of this kind of quantum dot means that they actually have the quantized energy level, because to emit any kind of photon, then that means that there should be some kind of discrete energy level. And then the advantage of the quantum dot or MV center is that they are based on the this kind of solid instead of the single atom. And then the fabrication might be more convenient compared to this one. However, because they are also surrounded by all the other atoms, which are not which are the part of the solid, but you cannot actually control all the other surrounding atoms. So there might be also some kind of noise. So that's the part that you should be careful when you are implementing this kind of quantum computing out of this kind of solid state based quantum computing. And then sometimes people are actually making a pattern like this one to create the quantized energy level. So still even though this might not look like a single atom, people can still make something very similar to the atom, or we can say that it is an artificial atom. So for both superconductor and then solid state based quantum computing uses the kind of artificial atom. So And then there are several ways to implement such kind of artificial atom using the solid state. And then this is one example, and this is another example, something called as MV center. MV means that nitrogen vacancy center. And then what that means is, what people do is use the diamond crystal. And then you know that when diamond, well, diamond means that actually they are always in the this kind of lattice. And then in principle, perfect diamond won't have any kind of vacancy. Vacancy means that um, because the lattice is periodic structure, so there should be always some carbon in each of the site, but there might be well, yeah, here, yeah, there should be carbon to make a complete diamond. But sometimes, yeah, inside the diamond there are some kind of vacancy, meaning that it is this side of the lattice is empty, and then it is called as a vacancy. And another part is also replaced by the nitrogen. So that's why it is called as nitrogen vacancy center. Center means that, yeah, around somewhere, not everywhere, but only around somewhere. Yeah, we will have this kind of defect. Yeah, so yeah, in a solid state we call this kind of situation as a defect, because in an ideal diamond, both of these sides should be filled with the carbon, not the nitrogen, or empty. Yeah, so that's why it is called as an empty center. And then if you have this kind of structure, then it is almost like having some kind of additional atom, and then around this area the energy level becomes quantized again. So this kind of configuration can also create the artificial atom, or more likely two-level atom. So that's how you people can implement the quantum computing, or the qubit necessary for the quantum computer. And then yeah, there is actually big difference between photon and the other three. And then we call, you can understand why we call the photon as a flying qubit, because a photon cannot just stop. Yeah, they should always fly away. And then the rest of them are called as a stationary qubit. And then now you can also see why it is called as stationary, because compared to the flying qubit, they are basically fixed in terms of the location. Yeah, even though, yeah, for these atoms we can move a little bit, but that such kind of movement is not critical. And then what is more important is that when I explained about the quantum circuit, yeah, I generally started with this kind of circuit. And then I also emphasize that even though this kind of circuit shows like the it is a two-dimensional layout, there is no such kind of thing as this kind of wire. And then it is representing the flow of the time. So as we move from the left to the right, that actually means that the time goes on. And then we just apply this case as um, as the time lapses. However, for the photon, it is complete opposite case. For the photon case, we actually draw this kind of path for the photon. So if you are familiar with the concept of the optical fiber, then yeah, I also showed you the example of the optical fiber when I explained about the quantum key distribution system. And then in that case, the photon is actually flying through the flying inside the optical fiber. And then this is not exactly fiber, but we can also make a very similar structure, similar to the optical fiber on the chip, or some other way. So what this really means is the spatially drawn path for the photon. So yeah, so even though we use the same circuit, quantum circuit picture, photon means that these are really the space, and then the photons are flying through this path, while for the rest of the stationary qubit, this circuit implies that from left to the right means that the time is ticking. And I don't know how much you are expecting for the quantum computing industry, but surprisingly enough, this slide was made like 2 years ago or 3 years ago, and at that time there are already so many of the a company who are making the quantum computing hardware and then software and consulting hardware, and then even the funding agencies. So yeah, investment. Yeah, I should say that. And then yeah, I cannot cover all these hardware company, but I will explain some of the companies which is also working on the quantum computer hardware. And then there are several big IT companies like Google or IBM, even Intel. Well, yeah, Intel is not really fully involved in the quantum computing, but they are also interested in the and then they are partially involved in the quantum computing, and then the Microsoft was also one of the one of the company who were supporting the quantum computing for a long time. And then yeah, there are also many ventures like IonQ or D-Wave, and then Rigetti or Alpine quantum technology, and there are so many. So yeah, I will just briefly introduce some of the company and then how they are doing their business or how they consider their own system. Oh, and then before I also discuss about the hardware system, let me also explain what these companies are doing. So these companies are claiming is that they are doing the software and then consulting. And then yeah, if you are not familiar with the IT consulting industry, then it might sound a little bit different area, but but inside the quantum computing industry, the consulting is one of the critical issue because as you already learned up to now, you realize that the algorithm of the quantum computing or the program, the way you program or the way you design your algorithm will be quite different from what you regularly expect with the conventional IT company, IT industry, and then unfortunately, many of the people who are already in the IT industry does not have enough time to learn this kind of class. They actually don't want to learn each of these concepts by themselves, but they actually want to achieve their goal by asking some other people who are knowledgeable about this area. So at this moment, software is not so popular, maybe, yeah, because the hardware is still limited in terms of their capability. But many of the IT industry company are interested in how to utilize quantum computing concept in their future technology development. So that's why they need a lot of consulting from those who has some background knowledge in this area. And then I hope many of you in this class can also be as work as such kind of consulting or interpreting role. So there are already several companies who are providing the quantum computing cloud service. And then yeah, this is, of course, incomplete list. And then the reason people are using, people are providing the cloud service for the quantum computer rather than like most of you expect like a desktop is because quantum computer currently still has a lot of errors, and then it also takes a lot of space. So the level of the technology is not as mature as you'd expect, and then such kind of level won't be reached within 10 to 20 years or 30 years. So what you'd expect is that they would like to maintain the performance of the or the system by themselves. And then what as a user, what you really want is to use the quantum computer as a service. So your cloud service will be as good as just having the computer on your home or in your room. So anyway, for such kind of reason, there are already several companies who are providing the cloud service, and then the probably with more complete list, you can also check here. And then even though different companies are providing different services, they still have, most of them still have the similar structure of their computing cloud service. And then it is also similar to what you would expect with the classical cloud service. And then as a user, you would use it, and you will interface with the front end. And then there are two types of front end currently. Yeah, one is the web interface, and another one is a programming API. And in today's lecture, at the end of today's lecture, I will show you some of the web interface provided by IBMQ. And then for the backend, there are several options. And then the first thing you would expect is the real physical quantum device. And then in this case, you can access this kind of device either using the web interface or the programming API. But you realize, as I explained, the number of the maximum qubit usable with this kind of physical qubit is not so many. Or sometimes some companies are providing a physical device with more than 50 qubits. But in that case, it is very noisy, and then it is so as you learned about the quantum error correction. If you have a lot of errors, then you have to actually use a lot of qubits to correct those quantum error. And unfortunately, at this moment, the level of the quantum error is so huge, so it is not correctable yet. So that's the part people are currently working on to improve, because without controlling the amount of error lower than some kind of threshold, you won't be able to correct. Yeah, you can imagine that if you have some device which is causing the error like 30% or 40%, how can you correct those errors? So yeah, so that will be almost impossible. So the first thing people are working on is to reduce the physical error as much as possible. So in the meantime, the physical quantum device might not be as useful as you would expect or you would hope. So another option is using the quantum simulator. So what quantum circuit simulator means that, and then later you will I will also sorry, I actually shouldn't call this one as a quantum simulator, because quantum simulator means something different. And then here, what it does is the quantum circuit simulator. And then what quantum circuit simulator is, yeah, for example, in the class, I already showed you several different types of the quantum circuit. And then when we are expecting or calculate, when we were calculating the result of each of the gate, we actually didn't use the real quantum device, but we can, in principle, calculate or expect the result of those quantum circuit. So, and then if the number of the qubit increases, then the amount of calculation will, or complexity of the calculation will become larger and larger. And then in that case, using the classical computer will be helpful. So so quantum circuit simulator means that the classical computer will calculate the result of each of the quantum circuit. And then this is not possible when the number of the qubit increases. And then I will also explain those such kind of situation in the next pages. And then, but in principle, with the at the level of 30 qubit each, then in principle, the classical computer can still deal with those, still predict the result of the quantum circuit. So those are called as a quantum circuit simulator. And then if you are using the, generally the cloud service provide such kind of calculation option as a backend of they provide those services to the user. But in some cases, for this quantum circuit simulator, it only requires a classical computer. So in many of the cases, you don't want to submit your job to a remote server, but you can just use your the computing power of your local PC. So in that case, you can either choose this remote server or the local PC, and then such kind of choice can be made at the programming API level. So that's how the current quantum computer model is provided. And then again, I will just show you the first option using the web interface and these combinations. Using the web interface, I will show you how to use these options at the end of today's lecture. So and then before I give you the more concrete example, let me just give you a few overview of different services. And then the first example is the micro Azure service. And then they recently started to provide their own quantum computing service these days. And then they also developed their own quantum development kit, and then they are using, they also redefine the C Q# language, and then you can also use some of the quantum circuit simulation, and then so such kind of quantum circuit simulation will be using the classical hardware, but in principle, you can also use other types of the hardware. And then what Microsoft Azure is currently supporting is two types of the technology. And then one type is called as ion trap technology, which I already explained in the first page. And then there are also several companies who are developing the quantum computer based on the ion trap. But Microsoft is providing the access to these types of these two companies who are based on the ion trap. And then another company which is called as QCI, and then their technology is based on the superconducting qubit. And then because these are different types of backend, and at the level of the programming or API level, in principle, you should be able to choose these different backend hardware. And then Microsoft by themselves has been also working on something called as a topological qubit, but the technology related to the topological qubit is still in its early stage. So yeah, it will take a while until we can consider using topological qubit. And then if this one works, then it will be great, because this one intrinsically corrects the quantum error. But on the other hand, it is very theoretical and the conceptual, so it's not clear when the topological qubit will be really available, or whether this will really succeed. Yeah, so we have to see what will happen in the future. And then in this case, again, Microsoft is developing their own hardware, but it is still far away. So currently, most of the services are provided through these other companies. So they are just providing the programming interface to these machines, but they do not provide the hardware service by themselves. Another option is the Amazon bracket. So oh yeah, there was typo. There is no C. Yeah. So what you can do is yeah, and then you can see why they call their service as the Amazon bracket. Yeah, by now. And then the model is very similar to other options. So yeah, what you do is, but the advantage of the Amazon bracket is that they are you can access this quantum computer service using the same interface like AWS interface. So once you log into their server, then in principle, yeah, you can just program the quantum circuit software, or you design your own circuit and then test it using the quantum circuit simulator, or yeah, you can use either your local simulator or the remote high performance circuit simulator, and then all of these tests are done with the classical computer. And then once you are comfortable with your circuit, then you actually want to run such kind of circuit, or such kind of circuit or the algorithm on a real hardware device. So they also similar to Microsoft Azure service, Amazon Bracket service also provide access to different types of the quantum computer hardware. And then the first guy is called as Rigetti computing, and then they are they are using the superconducting qubit. And another type of the qubit was the ion trap. Yeah, I already mentioned several times. And then you can see that the same company, yeah, IonQ, was used in both the Amazon, and then yeah, here Azure is also providing the access to the IonQ, and also the AWS bracket also provide the access to the IonQ. And then also, yeah, one of the special service compared to other options is that the Amazon bracket also provides us access to the D-Wave, which is called as quantum annealing. And then the concept of the quantum annealing is quite different from what we learned up to this point. What we learned up to now is we always described our circuit in terms of the gate. So yeah, these are called as circuit-based or gate-based quantum computing. But quantum annealing is uses completely different type. And then because I have a limited time, so I cannot cover what does quantum annealing means. But maybe at the end of the semester, once if I have some time available, then I will also cover what does how does the quantum annealing works. And then again, as I mentioned before, yeah, IonQ was one of the company who are developing the quantum computer using a trapped ion. And then, yeah, one of the interesting recent claim is that they claim that they can reach the quantum volume of 4 million. And then you might realize that how much this, yeah, and you maybe at this point you might not realize how much this is, how large this is, but I will also explain. I will also show you the amount of quantum volume the superconducting qubit can achieve. Then they are much smaller than this one. It is more likely just a few hundred. And then what IonQ believe is that their quantum volume is already too large. So just using the quantum volume by itself is not so efficient. So they also propose that we should use a new type of the metric, which they called as algorithmic qubit, and that is basically logarithmic 2 of the quantum volume. So oops, sorry. So in this case, what they are claiming is that their current quantum volume, which is 4 million, is corresponds to about algorithmic qubit of 22, and then this is their roadmap, which was obtained by from this link. And then, as you can see here, they are planning to increase the number of the qubit or algorithmic qubit linearly, but at some point they expect that they can increase the number of qubit more likely exponentially. And the reason they believe that they can do this is from this around this area, around this time, they think they can actually implement the error correction encoding. So once we can do, because currently the physical hardware is still quite noisy, and then you will see how noisy those physical qubits are. Yeah, because in the at the end of today's lecture, I will give you a demonstration, and then in the next lecture, I will also compare the noise level between different services. So these are the expectation, and then yeah, again, I'm my research area is the quantum computing based on the trapped ions. So I hope that this technology will excel all other technology. But yeah, we should also see how these different technology will compete with each other, and then see which will be more appropriate for your own application. Another company I should not forget to mention is the Google, and then Google has been also investing on the quantum computing for a long time, and then they also provide their own programming framework based on Python, and then it is called as a circuit. And then you can, if you are interested, you can also check the content of the or the more information about the circuit. And then the different, compared to all the other companies which I mentioned in the previous pages, they still do not provide access to their own machine to anybody. Yeah, so yeah, they allow the access to their company's hardware only for the limited number of people, but it is not open for the public access. And then but they also demonstrate the performance of their own hardware almost 1.5 years ago, or at the end of the 2019. Yeah, they demonstrated something called as quantum advantage, or sometimes it is called as a it used to be called as quantum supremacy, but because the terminal the word supremacy sometimes might imply some kind of discrimination. So people prefer nowadays to use, or are careful in using this kind of terminology, and then many people just recommend using the quantum advantage as the word. Anyway, yeah. So another option or another framework Google recently not by now, yeah, it's almost 1 year ago. Yeah, what Google introduced was the combination of the TensorFlow and then circuit. So their intention is to allow that people can utilize the performance of the quantum circuit or quantum computing to study the machine learning, or vice versa. When we are developing the quantum technology, we can also use the capability of the TensorFlow or machine learning. So these are the options they are providing. And then I will actually explain more about this result of their demonstration of the quantum advantage in the later page. But before I explain this one, let me first give you the idea about the quantum simulation. In the previous discussion, I mentioned about the quantum circuit simulation using the classical computer. So even though even though I said that simulation of quantum circuit in classical computer is possible, but there is a serious challenge. Let's estimate how much memory do we need to simulate such kind of situation. So let's say that let's assume that we have some very simple quantum computer which has only 2 qubits, and then we want to simulate the situation where the quantum circuit. We want to simulate the quantum circuit which will be applied to this kind of hardware. Then how many memory do we need? Well, yeah, we know that any arbitrary quantum state can be should be or will be represented as the summation of all the possible bases, and then the number of bases will increase as the power of 2. So if we have 3, then we will have 8. We will have 8 bases, and then if we have 8 qubits, then we will have 256 different bases. And whenever we have different bases, then that means that we have to, during the calculation or during the simulation, we have to keep all the coefficient value in front of each of the basis vector. And then how much memory do we need to keep all of these coefficient? You know that this value is basically continuously changing, meaning that this will be analog value. So to keep the accurate analog value in the computer, we cannot just use the integer, because integer will have some limited range. So the most reasonable choice is that we have to use the floating point, and then there will be different options like a single precision or double precision. And even for the a single precision, we need at least 4 bytes. But remember that this value is not just the real value, but it is a complex number. That means that we actually need to store 2 of the real numbers. So we will eventually need order of about 8-byte memory to store each of the coefficient. And then how many memory do we need? So we have to calculate like 8 times 2 to the second, and then like this one. Then what about storing the quantum state of the 50 qubit? Well, then we have to calculate in this way, and then we know that this can be split into this way, and then 2 to the 10 is 1024, which is approximately 1,000. And then if we calculate in this way, then the 10 to the 15 bytes corresponds to petabyte. And just in case you are not, you don't know how large is the petabyte, then we can compare such kind of amount with the rank 1 supercomputer in the world. Yeah, so in the supercomputer area, people are ranking the power of or performance of the supercomputer in the world. And then as of the last year, November, the rank 1 supercomputer is, the name of the supercomputer was the Fugakyu at Riken Research Center. And then if you check of the specs of the Fugakyu, then it has a memory size of 5 petabyte. So even the top rank 1 supercomputer has the memory size of only 5 petabyte. However, I said that to represent the quantum state of the 50 qubit, we need 8 petabyte. So even the top 1 supercomputer cannot hold all the necessary coefficients for the 50 qubit. And the situation gets worse. What happens if I just add 1 more qubit? Then the overhead to represent the 1 more qubit is not just the 1 or 2 petabyte additional 1 or 2 petabyte, but it's actually another 8 petabyte. And if we increase another qubit, then it will become 16. Then the required number of the memory will be 32 petabytes. So the required memory size increases exponentially as we increase the number of qubits. So this is not scalable with the classical computer. So that's why we need to consider some other strategy, and why, and then you can see why it is so challenging to simulate the quantum circuit using the classical computer. And then if you remember that the size of the memory in your typical laptop or in your desktop is order of just gigabyte. So that one so maybe 4 gigabytes or 16 gigabytes will be probably the typical number on your desktop. So that means that we can only store about 30 qubits. So that's the reason why many of the quantum simulator supports only up to order of 30 qubits. And then to support up to 50 qubit, we really need a high performance computer like a supercomputer. Then what will be the challenge? What is the alternative way to solve such kind of problem? And it is called as a quantum simulation. And then this is completely different from what I just mentioned in the previous page, which was the goal of the previous page was the calculate the result or predict the result of the quantum circuit using the classical computer. But we realized that the calculation of the quantum mechanics or quantum phenomena on a classical computer is really challenging. And then the more obvious example is like quantum chemistry or solid state physics. Let's say that you want to solve some kind of quantum chemistry problem. And then the problem is in chemistry, chemistry involves a lot of handling of the many of the atoms. And then in that case, the unfortunate problem is that each of these atoms follows the quantum mechanical rule, not the classical mechanics. So all the problems we have been considering will be still applied to this kind of situation. Yeah, so let's consider some more concrete example. I don't know how many. I assume that some of you are not comfortable with or familiar with the concept of the spin, but spin is some kind of fundamental property of the most of the particle, like an electron or the nucleus has its own spin, and then you might consider that the behavior of spin is similar to magnet. However, because it is working in the quantum domain, so the direction of the this particle, this spin cannot be some continuous value, but it is more likely down or up. However, because it is following the quantum mechanical rule, it also allows the superposition of down and up. So how can you solve the problem involving this kind of spin? If it is just a few spins, then it is not so difficult, because all we have to do is, if there are only two spins, then all the possible combination is down, down, up, down, or the up, up. So there are only 4 possibilities. However, if if our problem involves order of 50 spins, then what's the problem? Then the possible combination of the spins are like order of 2 to the 50, which is 10 to the 15, which we already checked. And then the most challenging problem is quantum mechanics allows the superposition of all those combinations. So now we have to consider all of those problems, and then basically solving such kind of problem using the classical computer is almost impossible. Then what is the other option? Well, let's think about the analog. What is something called as analog simulation? In this case, our challenge is, let's say that this is some kind of mechanical system. So it might have some kind of damper and then mass and then spring. And then if you solve the governing equation of this kind of mechanical system, then you will obtain this kind of second order differential equation. And then, of course, this problem by itself is easy to solve. But let's say that we have not only these 3, but there are many of the dampers and then the spring and many different masses. So the order of the differential equation is not so straightforward, but it becomes more and more complicated. In that case, what we have to do is and in that case so instead of solving the this differential equation, you might just choose to simulate or test this kind of system, and then you are trying to optimize this kind of system with the proper K or proper damping constant B or some different mass. And then if you know about the mechanical system, then changing the mass actually requires the some kind of machining. Or if you want to try different spring constant value, then it will also require a lot of additional work. However, if you note that this kind of system can be the solution of this one is almost exactly the same as the solution of this RLC circuit, because if you have this kind of RLC circuit and then write down the differential equation corresponding describing this system, then it will also turn into the second order differential equation. And then solution of this mathematical solution of this equation and this equation should be identical as long as you have the same coefficient in front of it. But the benefit of this circuit instead of using this one is that, as I mentioned, to try different spring constant or different mass requires a lot of extra work. While for this case, all you have to do is just replace the resistor with different value. And then for the resistor or capacitor, there are just a set of resistors or capacitors, and then you can just replace them without any trouble. So even if your final goal is to understand the behavior of this system, in principle, you can just use something which is much easier to deal with or play with, and then and once you obtain the solution of this equation, then it is equivalent to obtaining the solution of this one. And such kind of concept can be also applied to this one. So we know that the challenge in this case is that each of these particles or the entire system of these particles follow the rule of the quantum mechanics. However, the quantum computer is based on also on the principles of the quantum mechanics. So, and then the benefit of the quantum computer is that each of these qubits are manageable compared to these spins. So instead of trying to directly solve this problem or directly trying to implement this kind of system with the physical material, if we have a very good controllable quantum system like this one, which can be considered as a quantum computer, then each of the quantum state of this one can be directly mapped to each of the qubit. In this case, of course, making a quantum computer with 50 qubit is still a challenging job. But once we make this kind of thing, then whether we have the spin or some other quantum material, still all of them can be, in principle, simulated by this system. So it is almost like instead of using this mechanical system, we just use this electrical system. So instead of trying to use this, instead of playing with or doing the experiment with the real material, we can just simulate using the more controllable system like a quantum computer. So such kind of concept is called as a quantum analog simulation. So this is one of the active topic in the quantum computing and the quantum simulation area. But because this class mainly focuses on the quantum information part, quantum computing part, so I will just stop the introduction of this concept. However, one of the reasons I mentioned about such kind of concept is because it is actually related to the quantum advantage experiment, which was demonstrated by Google. So around the end of 2019, Google published a paper claiming that they demonstrated the quantum supremacy, or I said that, let's say that, or I will just call it as a quantum advantage using their own quantum computer. And then they basically built quantum computer composed of 53 superconducting qubits. So in this case, the way they implemented their quantum computer is using the superconducting qubit instead of other atomic-based qubit. And in this case, each of these, as this legend shows, this cross basically represent the qubit, and then this blue thing means the interaction between these two qubits. So what they did was, and then this is the zoomed in image of this this kind of situation, and then the number of the qubit here is the 53 because one of them is broken. So yeah, that's why they just use the 53 qubits. And then in this case, what they did was, because now this one, this kind of thing represent the real hardware, and then we know that this qubit and this qubit is connected through some kind of interaction. Yeah, it is called as an adjustable coupler. So it can be turned on or off. And then, yeah, when this coupler is turned on, then that means that these two qubit will have will perform some kind of two qubit gate. While if there is at another time, they will just turn off all these coupler, then they won't, there won't be any interaction. And then later they might just turn on this coupler or the other coupler. Then in principle, they can implement or execute this kind of circuit on this hardware. And then what they proved is that if they just try some random circuit, yeah, so yeah, this circuit doesn't have any computational meaning. So it does not have it. This current circuit does not correspond to any of the quantum algorithm, but they just randomly choose the circuit. And then the question is, if we provide this same random circuit to the classical computer, can the classical computer predict the result of the entire circuit? And then the answer was, if they just provide all of these circuit scheme to the this real hardware, then all they have to do is just turn this coupler on and later off, and then turn the other coupler on, and so forth. So the amount of time to go from here up to all the way to down is increasing linearly. However, if we are just trying to calculate what will be the final quantum state, then the challenge is that because the number of qubits are more than 50, so we to hold all those coefficient information in the classical in the memory of the classical computer, then it actually requires more than the number rank 1 supercomputer. And then that's based on such kind of limitation, they estimated that to solve the problem corresponding to 53 superconducting qubit problem on the classical computer, it would take more than 10,000 years. While if they just try to estimate the result of this one using their real hardware, then it would take about 200 seconds. And then 200 seconds is not just the time to execute this one from here to here, but let's say that if you have some kind of output state like alpha alpha 00 plus beta 01 state, Then to make sure that we don't have any of the coefficient like this value is 0 and then this value is 0, then what we have to do is repeat making this kind of preparing this kind of quantum state over and over. And then whenever you prepare this kind of quantum state, then you measure it. Then if this quantum state is properly prepared, then we will always obtain either 0, 0 or 0, 1, and we won't obtain any of it 1, 0 or 1, 1. So based on, and then yeah, if you repeat such kind of experiment over and over, yeah, so experiment does not just include the measurement, but you start from the initialization and all the way up to the measurement, and this is the one cycle. And then in that case, you will either obtain 0, 0 or 0, 1, and then you run it one more time, and then you will obtain one of these. And then to figure out the amount of alpha and beta, then we have to repeat this kind of trial so many times. So yeah, if you just repeat that many of time until you have enough confidence that the ratio of the alpha and beta of such and such, and then make sure that these coefficients are very close to 0, meaning that you won't measure any of these events, then you can be sure that the result of this circuit will be such and such. And then all of those process will take about 200 seconds because you have to repeat so many times. However, to figure out this kind of ratio using the classical computer, then again, what you have to do is first allocate the memory which is large enough to contain all the necessary coefficient, and then it will take more than several petabytes. So yeah, it will be almost impossible to do that with the regular supercomputer. So that's why they could claim that it would take so many years. However, a few days later, IBM also challenged such kind of claim that if they design their classical algorithm on a classical computer, or the more exactly, they claim that if they use the second storage like a hard disk or the flash disk, and then if they make a clever scheduling scheme, then they could in principle simulate or calculate this kind of problem within just a few days. So and then yeah, so there has been a lot of active research in how to reduce the necessary time to predict output of these random circuit. But the point here is, and then if because this is a random circuit, it has nothing to do with the quantum algorithm like factoring or Grover search. And then so this is kind of waste of computing time if you are just trying to figure out the result of this kind of random circuit. But the reason people were so interested in this kind of problem is it actually corresponds to the validity test of the extended Church-Turing thesis, because according to the extended Church-Turing thesis, if you don't consider the quantum computer as a special case, then what this claim is that the probabilistic Turing machine in principle can efficiently simulate any process on a realistic physical device. However, as this example shows, this kind of a randomly created circuit cannot be efficiently calculated or simulated on a classical machine. So even if the classical machine has the option of some probabilistic Turing machine, still it's not enough. And then if the and then the point of this experiment is that to simulate any process on a realistic physical device, then we need to change this probabilistic part to the quantum. And so this extended Turing thesis should be modified, and then it should be read like a quantum Turing machine can efficiently simulate blah blah blah. Yeah, so that's the reason why people are interested in the quantum advantage. And then finally, I want to actually point out that even though this experiment or this demonstration used the concept of the circuit, the actual meaning of this experiment corresponds to more likely the quantum simulation, because what the challenge in this problem is, how can we simulate, or how can we predict this kind of problem or some other problem more efficiently using some other options. And then so the challenge in this case was corresponds to and then the challenge in this case is exactly the memory limit, the number of the memory limit. So even though the question in this case seems to be the problem of the circuit, some kind of algorithm issue, but it is not. It is actually just trying the quantum simulation problem on this machine. Another recent news article, if you were interested, then around the end of last year, there was also another news about the quantum advantage. And then what the news said was the USTC group published a paper claiming that they demonstrated quantum advantage using photons. And then according to that claim, their speed up compared to the supercomputer was factor of 10 to the 14th. So it's a huge challenge, huge improvement. And then but I should also point out that the challenge or the implementation, the picture of their implementation looks like this one. And then as you can see here, as it is saying, it is based on the photon. And then as you can see here, this is beam splitter. And then these are the mirrors, and then these are all fibers. And so if you look at this entire setup, then you would not consider this one as a computer. However, the meaning of this experiment is the following. So this experiment, what this experiment was trying to show was that this kind of physical system can solve or predict the result of boson, something called as a boson sampling problem. And then the reason why this problem is interesting or challenging is that they use like a 70 photons, and then even though if you just look at this picture, then you cannot understand what it is doing. But all it does is it creates it generates multiple photons, and then send those photons along the optical circuit. And then inside that circuit, there are so many options of the paths. So at the end of the such kind of propagation, it's not easy to predict which output port the photon will come out. Yeah, let me give you a little bit more concrete example. So something like if you have only two photon and then two paths, then in principle the photon can start from here, and then it has an option to either going in this way or pass through. And similarly, this one has either going through pass or going the other way. However, if we make more paths, optical paths, and then and if we have another path, and then later these two paths will be also mixed, and then another path will be also mixed with another one, and something like this one. And then once you have so many of the paths like here, then at the end of the day, it is not easy to predict how many photons will come out. And then especially one of the reasons why it is called as a boson sampling is that the boson is some kind of property of the particle. Yeah, then all the particle, any of the particle should be should be classified between the boson or fermion. And then boson, if the particle is considered as a boson, well, yeah, the photon is actually the representative example of the boson. And then boson type generally has its own special property. And then if we consider such kind of special property, then prediction of the output of this kind of problem becomes extremely challenging. And then the predicting the result of this output actually corresponds to the calculation of permanent of matrix. And I assume that many of you are not familiar with the concept of the permanent of the matrix. So, but you know that what does the determinant of a matrix mean? So if you are given this kind of a matrix, then you will have sometimes in front of the term it becomes plus, and then sometimes it becomes minus. And the permanent of the matrix is almost similar to the determinant, except that there is no minus term. Every sign will be plus. And then surprisingly, calculation of the determinant of a matrix has a relatively efficient algorithm. However, calculation of the permanent of a matrix does not, there is no efficient algorithm to calculate this kind of permanent, this kind of property. So yeah, and then yeah, practically there is also no good application of the permanent. So that's one of the reasons why people were maybe not so interested in the problem of the permanent. But the point is, yeah, this problem is already very difficult. However, if you just make this kind of circuit using the physical device and then send down the many photons like this one, then all you need to do is just measure at the end of the port, and then based on and then your measurement result will just tell you what is the value of this permanent of the matrix. So that's why they can claim that they demonstrated quantum advantage. But similar to the Google's demonstration of the quantum advantage, it simply showed that the extended Church Turing thesis may be modified to the quantum version, but the problem, the result or the calculation result of this demonstration actually does not have a well-defined physical meaning or the practical purpose. Yeah, so yeah, this is still kind of scientific demonstration that quantum computer will probably have a better performance compared to the classical computer, but this one is not so useful for the practical application. Finally, let me give you the overview of the IBM quantum system. Yeah, among all those companies, IBM was probably the first company who actually made their quantum computer available online, and then yeah, that's and therefore they have various support for the use of the quantum computing. And then, as you can see here, yeah, they have well-defined website which also explains various aspects of their computer. And then another thing, yeah, which I will introduce today is the online graphical quantum circuit and editor and their access using the this web interface, which I mentioned in the early today. So what I'm going to do is first I will run the using in today's lecture I will just use the web interface and then show that the quantum circuit can be simulated either using the classical computer, or we can also see how does the quantum device performs by submitting the job to the quantum device. So and then one thing I also want to point out is that this is the roadmap of the IBM, and then as you can see here, their number of qubits, the number of qubits in their system are much larger compared to the IonQ, which I showed you before. But surprisingly, their quantum volume, achieved quantum volume using these 27 qubits are quite small compared to the IonQ. So if we just convert this quantum volume back to the algorithmic qubit, which was explained in the by this IonQ formula, then their corresponding quantum volume is only 64 at 128, which was the result of last December. One thing I want to point out here is the number of qubit is not a good metric to represent the performance of the system. And then it is not clear how we should convert the result of the Google's case. So here they claim that they demonstrated the quantum advantage using the 53 qubits. So, but in the paper, they never mentioned about the quantum volume. So it is not clear exactly what will be the corresponding quantum volume will be. But again, I want to point out that the number of qubit might be a little bit misleading factor. So when we are testing when we are comparing the performance of the quantum computer, then you should really be careful when you are selecting the selecting the technology for the quantum computing. Anyway, so IBM already has the very nice web interface. So let me just introduce this one. So if you go there, then probably you don't have the IBM account, so you have to make one. And for my case, I already made one, and then so I can just log in using my IBM password. And then here, what you can see here, the first thing you can see here is there are various menu, but maybe this might be one of the interesting part. So currently my account is a free account. So there are even though there are 26 systems, I can only access the 13 of them. And then probably within a few weeks, students at the Seoul National University probably will be able to use all of these. So you have to wait until I will give you an announcement, but or someone else will give you an campus-wide announcement. But the point is, currently we cannot use more than 15 qubit. So this is the system with the largest number of the qubit. But surprisingly, as you can see here, smaller number of qubit system has a higher quantum volume, because as the number of the qubit increases, then as you can see here, if you look at the configuration, the layout of the qubits, then these qubits are connected to each only for example, this qubit number 1 is connected only directly to the 0, 13, or 2, and then there is no other connection, a direct connection. So if you want to implement any kind of CNAT gate between qubit number 2 and 9, then what you have to do is apply the swap gate. Yeah, we already learned about the swap gate several lectures ago, and then if you just do swap, 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 then they will be next to each other. Then you can apply the CNAT gate, for example. So having the multiple more qubit does not necessarily mean that you will have the better performance. However, for this 5 qubit case, even though the number of qubits are small, but the quantum volume was higher. So yeah, don't be fooled by the number of the qubit. Yeah, again. And then inside here, and then if you check the even more higher case, then they also achieve the higher quantum volume with the 27 qubit. And then in this case, the configuration looks like this one. On the other hand, the largest number of the qubit is 65. And then here, yeah, they don't have, then they don't have the quantum volume. But here it has only 32 quantum volume. So again, in this system, it might look like it has a lot of qubit, but in terms of the performance, yeah, they might be less powerful compared to these 27 qubit systems. So yeah, anyway, yeah. So let me go back to the my available system, and then here the distinction between the above one and the below one is these are all about the quantum circuit simulator, which will be executed on the classical computer. So this kind of system is useful when we are estimating the as I mentioned before. So the lower part corresponds to this quantum circuit simulator, which was run on the classical computer, and then the upper part was corresponds to this real physical quantum device. Oops. Yeah. So this is just an overview of the system. So what I'm going to do is I will show you the how we can use this system. So the first thing is you have to make a new circuit, and then if you start with this composer, then you will start with this empty circuit, and then let's say that we want to create the quantum state, something like something called as a GHZ state. And then the definition of a GHZ state is something like 00 plus 111, like this one. Then how can we implement this kind of circuit? Well, the first thing is that and then let me even though we started with all these 3 qubits, there are several ways you can increase the number of qubits. You can either press this, or there are also manage register, and then we can also increase the number of the qubit. So let's say that we will start with the 5 qubit. Then what is this classical register? Classical register means that when we measure the value of the quantum register, then that measured result should be stored somewhere. So that is the purpose of the classical register. So there will be generally the same number of the classical register will be required when we increase the number of the quantum register. So now I created, I increased the number of the quantum qubit to 5. And then what I want to do is, because I want to create this kind of quantum state, what I have to do is first apply the Hadamard gate here, and then once the first qubit became the superposition of 0 and 1, then I can apply the controlled NOT gate from here to the 1, and then another controlled NOT gate from 0 to 1, from 0 to 2. Oh, by the way, here the numbering of the qubits are from 0 to index of the qubits are starts from 0, and then they just increase. And then how can I draw? Well, that is very very intuitive. All I have to do is pull the symbol from the library, and then they will just create like this one. Then if I just do that, then this will be created between only 0 and 1. But if you double click this one, then you can actually choose the target qubit number. So currently it is qubit 1, but you can just connect to the qubit 2. So that's how you can create your first circuit. And then now what I have to do is once we run this circuit, then I have to also measure the result. So we also put the measuring device like here, and then as I mentioned before, once we measure the value of the qubit, then the qubit will collapse, and then the measured result will become the classical value. So all the corresponding value will be stored in this classical register, and then we will keep measuring all of these three. So this in principle can be run, but yeah, let me give you a little bit more tricks with this composer, or the generally for this circuit. So let's say that the fourth qubit, or qubit number 3, doesn't do anything, but let's say that we still want to measure the value. And then if I'm just trying to put the measurement directly here, then as you can see here, it does not go there, because theoretically the result of this circuit, or whether this one sitting measuring this value after all those operation, they should be the same. So why not just waste the time? But in some case, you still want to separate or run everything until all the operation is over, and then you might want to measure it. So in that case, what you can do is put the barrier, and then if I just do this, that barrier will only apply to the first qubit, but we can increase the size of the barrier. And then now what I can do is move this one behind the barrier. Then in terms of the timing, this fourth qubit will be measured only after all these operation is done. So this is what I just created. Then how can I run this circuit? Well, yeah, then you have to go here. And now I have to decide my backend. And the first, as a first example, let me try the circuit simulator. Not the so as a backend, I will choose the classic circuit simulator running on the classical computer. So yeah, you can choose either probably one of these two, and then let me choose this QASM. And then as you can see here, there are this one shows how many jobs are waiting in the queue. And then yeah, here I just chose this one, and then what I have to do is, because what we are doing is simulating the calculation experiment. So when you start your computing, then the first thing you have to once you created your quantum circuit, then when you are running, the result you will expect is a single measurement. And then unfortunately, even though the state is expected to the superposition of 0, 0, 0 and then 1, 1, 1, if you just measure, you will only obtain one of them. Yeah, 0, 0, 0 or 1, 1, 1. But that does not give you the information of the entire quantum state. So what you have to do is prepare this one and measure, and prepare this one and measure, and so forth. So you have to keep repeating the creation of this one, and then each of the preparation, then you will have the measurement, single measurement. So the number of 1024 shots means that we will repeat preparation of the state and measure for 1024 times. So that's the number of the shot. And then, of course, if you increase the number of the shot, then the accuracy of these estimation will become more accurate. So accuracy will be increased, but the number of the time it takes to obtain the value will be also increased. So you have to choose some reasonable number, and then here the default value is 1024. So let's run this, and then and the job is queued, and then now I already obtained the result. So let's see what does the result look like. So if we open with the more detail, then as you can see here, so the same circuit, the same this quantum circuit was run for 4 times, not 4 times, but 1024 times, and each of them, it will either measure 000 or 111, and then in this case, the reason you see not just the 000 or 111, but it is called as a 00111 is because this circuit was composed of the 5 qubit, and then even though I didn't say that the 5th qubit should be measured, you will probably automatically measured, and then the value is shown here. And then you might be also confused because that these were the first 3 qubits, but they are shown in the least significant bit. So this one, you might say, you might think that this index corresponds to the power of the 2. So the first qubit corresponds to 2 to the zeros. Oops. Sorry. So this one corresponds 2 to the 0, and 2 to the 1, 2 to the 2, and so forth. So the 2 to the 4 will become the most significant bit here, and then 2 to the 0 will correspond to the least significant bit. In computer science, we call this one as LSB, least significant bit, and then this one as the most significant bit, right? So this might be a little bit confusing when you see this result for the first time, but I guess you can easily understand the situation. And then another part I want to point out is that we run the 1024 times, as 1024 times. Then you would expect that each of the result will come out with 512. However, you can see that the number of this 000 comes out only 506, while the 111 case came out more than 512. Why is this case? Because we are simulating the case. We are simulating the real experiment. And then in the real experiment, what is guaranteed is that the ratio between 000 and 111, where here 0 and 111, the ratio of the probability of the 000 and 111 are equal. But that does not necessarily mean that if you actually run the experiment, you will obtain such kind of 50-50. So if we run, if we increase the number of shots much higher than 1024, then you might get much closer to the 50-50. But with this number of the trial, then generally you would not get exactly 50-50 case. And then so this is exactly what you would expect if you run the experiment. So now what I can do is, instead of running this one as on the classical computer, let's actually run it on the real quantum computer. So there are many of the options, and then let me choose something which has least pending jobs. Yeah, for example, here there are too many jobs waiting, so I probably want to avoid. And unfortunately, there is not. Yeah, probably I should choose this one. Yeah, so if I choose and then run, yeah, I don't like this one because it has a low quantum volume. But all those, well, maybe I can try this one. Yeah, this one has the highest quantum volume. Yeah, so let me just try. And then now that job is scheduled, and then put in the queue. But it might take a while until we can get the final result. But and then in the meantime, yeah, and in the meantime, let me also explain some other parts. So here, yeah, another representation of this circuit can be also expressed in terms of the of something called as open QASM. So open QASM is, yeah, if you just read this source code, then you can immediately see what each of this means if you at least they have some experience with the assembly code. And then in this case, you just declare the number of the quantum registers, and then declare the number of the classical register, and then apply the Hadamard gate to the first qubit, and then apply the CNAC gate between the first and second qubit, and so forth. So this one exactly describes what appears here. And then this might be still useful, but as the complexity of the circuit becomes higher, then this is not efficient. So there is also other options to use the Python language. And then yeah, I will cover that part in the next lecture. But in today's lecture, yeah, we will just use this one. And then yeah, still this job is pending because probably there are a lot of other jobs waiting. Yeah, let me. Oh, now it is completed. So let's see how does the result look like. Okay, and then you might be a little bit surprised with the result. Okay, why is this? So yeah, in the previous quantum circuit simulator run on the classical computer, we at least got this one closer to 500 something. Yeah, because we are expecting that this 000 and 111 will come out very close to 512. And here it is 461, and this one is only 250. Why is this? That's because this circuit is this processor is very noisy, and then these are not the quantum state you would expect. But whether we want it or not, you obtain these. So you can see that this machine is very noisy, and then one of the reasons it becomes noisy is that it is also related to the configuration of the circuit. So the machine we run is called as IBMQ Essence. And then if we go back to the configuration, then if we click here, then we should be able to see the configuration of this circuit. So yeah, physically, this circuit looks like a so where is that? Yeah, so this is the hardware connection. So as you can see here, all the qubits are connected to each other. And then even though we initially drew this kind of circuit, internally it was converted to this circuit. And then as you can see here, the main reason it is changed to here is the 0 qubit, which corresponds to here, is the first qubit is chosen as this qubit, And then now, what it does is, this is the main qubit, and what we have to do is we first apply the CNAT gate between the control qubit and the target qubit. So now this first qubit is first one qubit is now mapped to the second qubit, and then what we want to do is we first want to apply the CNAT gate between the first qubit and the third qubit, and then now the limitation of this circuit or this hardware is that this first qubit is only connected to the third qubit. So, but because this control qubit should work on the at least 2 qubits, so instead of with the current configuration, you cannot apply the second CNAT gate on other qubits. So what is your option? Well, the simplest option is you just swap these 2 qubits. So first, it is this control is applied to the third qubit, and then you will swap these 2 qubits together. So what, as you can see here, after the application of the first CNAT, then what is this pattern? This one exactly means the swap gate. So the information stored in here is now swapped out to the second this qubit number 2. And now we know that the qubit number, the value of the qubit number 2 is swapped into the qubit number 3. And now what we can do is apply the CNAT gate again. So now even though this is now working on the third qubit, what really happened is that during the swap gate swap operation, the qubit is qubit went the information stored here went to here, and then the information stored here went back to here, and then now this control qubit changes the target qubit in 2, and then finally that value is measured like here. So one of the reasons why we can see a lot of noise or the error here is because even this simple operation requires a lot of swap operation. And then as the number of the qubit increases further and further, this problem will get worse and worse. And that's why we have to also consider the connectivity of your circuit. So again, the number of the qubit is not the good metric to compare different technology. And then maybe one of the reason I'm emphasizing this one is because the number of the qubit typically used in the ion trap might look smaller than the number of qubits used in the superconductor qubit, and then that's why the superconductor qubit has been popular among the IT industry companies. However, if you really look at the technology, underlying technology, then the ion trap is actually much better in many of the sense. And then you will actually see such kind of result in the next lecture. So in today's lecture, I will just stop here.